Okay, so number 10 over here, as you can see, is talking about a pizza shop owner determines the number of pizzas that are delivered each day, and they want us to find the mean, variance, and standard deviation for the distribution table over here. And they're saying if the manager stated that 45 pizzas were delivered on one day, do you think that is a believable claim? So remember, for our mean, variance, and standard deviation, you have different calculations. I just want to highlight those over here. So remember, for the probability distribution, we take each outcome and multiply it by its probability, then add them up together. For variance, you take the square of each outcome, multiply it by the probability, and then you add those together. And then from that sum, we subtract the square of the mean. And of course, taking a square root of the variance gives us the standard deviation. So let's start by finding the mean for this data set. So here's your formula for the mean. Let's go back to example 10 over here. Okay. Remember, that's summation of the outcome multiplied by the probability. So what do you think this mean will come out to be in this example? And remember, the rounding rules for these were you round it to 1 decimal place more than what your outcome is going to be. So what do you think that mean is going to come out to be? Okay, Lily, you've got 37.1. So remember, this is where you would be taking those number of deliveries. So 35 multiplied by its probability of 0.1, 36 multiplied with 0.2, 37 with 0.3, and so on. And then add all of those products together. So Alexander, you also came up with 37.1. Alrighty, very good. Same, Jesus, already, very good. So 1 decimal place more than our outcome. So yeah, 37.1 sounds good. And that's what I came up with as well. So now let's talk about variance. So let me write that formula down. So for variance, basically the same calculation that you just did, but instead now we will take our outcomes and square them, then multiply by the probability. So you will do this individually, then add all of those products together, and then finally subtract the square of the mean from it. So let me show you that formula one more time here. So this is the formula you're looking at. So first, we'll do the multiplication part first and add them together. So this part, so just for the x squared times px, what are we coming up with? So just taking x squared times px, because we know our mu is 37.1. So what does that x squared times px come out to be? Okay, Lily, you've got 1,377. Okay, did anybody else get that same answer? Jesus, 1,377.7. Okay, very nice. So what will that variance come out to be now that we have both of these numbers? Alrighty, 1.3. Let's see, so 1,377.7. You are subtracting 37.1 squared from it. Okay, very nice. Yeah, so your raw answer would be 1.29, which again, using our rounding rule, would round up to 1.3. So we've got our mean, we've got our variance. Now, when you're calculating your standard deviation, remember this is where we take the square root of our variance. So when you're taking the square root, take the square root on 1.29, and what does that end up giving you? Okay, Lily, you've got 1.14. Jesus, you got the same answer. Let's see. Yeah, so the raw answer I'm coming up with is 1.136. I'm guessing that's where you got the 1.14. And then using the same rounding rule, this will end up giving us, of course, again, one decimal place. So this will give you 1.1 as the standard deviation. All right, so this was finding our mean, variance, and standard deviation. Now, the question they are asking us, if the manager stated that 45 pizzas were delivered on one day, do you think that is a believable claim? So looking at our mean of 37.1 and our standard deviation of 1.1, what do you guys kind of think about those 45 pizzas in one day? Alexander, you are saying no. Lily, you are saying no. Okay. So for the most part, you are saying this is not possible that he would get an order of 45 days in one day. Can you think of any day when that might be true? Yeah, maybe if he had some bulk order for a party or something. Yeah, and you know, the one day we had looked at like Super Bowl snacks, which they hadn't included pizzas in that. But honestly, that's the only day I would think of any pizza place being like super busy. Because, you know, obviously pizzas is one of the sought after items like on a Super Bowl Sunday, other than chicken wings, I guess. So other than Super Bowl, I would imagine for a regular day, he is not going to be getting 45 orders of pizza, because especially when you look at this example here, we've got a mean of 37.1. So even with that standard deviation of 1.1, even if you go out 2 or even 3 standard deviations, we're not making it to 45 pizzas as any given day. So yeah, it's definitely a highly unlikely scenario. But like I said, maybe except, and even for a bulk order for a party, I mean, it would have to be a lot of people for them to order 45 pizzas. So, you know, it really depends. So we can just throw in there for, you know, like a Super Bowl scenario kind of thing. Alrighty, so just another example that I wanted us to look at in terms of how you can calculate your mean, variance, and standard deviation for probability distributions. Now, let's go on to our 5.3 over here. And this is where we're actually getting into the binomial distribution itself. So let me, I don't know what your textbook is. You should be able to, I can't actually remember where I got this document from, but let me see if it will let me send you guys a file over here. Because this file over here has the entire table that you guys need for this binomial distribution. So hopefully you should be able to download this on your end. If anybody is unable to download it, let me know. It should have 6 pages for, you know, the different calculations. And of course, we'll look at these examples. Just make sure you are able to get that table, okay? Okay, so binomial distribution, again, remember this is based on discrete probability distributions, like we had said with 5.1 when we started this chapter. So they're talking about how many types of probability problems only have 2 outcomes, or at least they can be reduced to 2 outcomes. So this is actually something that is crucial when you are talking about probability distribution with binomial distributions. So as an example, again, coin toss, you can see how it's only going to land on a head or a tail. So, you know, that would be a probability, type of a probability, which would only have 2 outcomes. So, you know, that's a classic example for 2 outcomes of a head or tail. Now, when we're talking about, you know, rolling a die with a 6-sided die, or, you know, even something bigger than that, you can reduce it down to 2 outcomes. So you can see with the die, we are talking about, does it roll an odd number or an even number? So again, we're breaking this down into 2 outcomes. With the basketball game, we are talking about either team wins or loses, right? So again, breaking it down into 2 outcomes. A true and false type of a question, of course, would also have 2 outcomes. So that's one thing which is very crucial when we're working with binomial distribution, is we have to be able to break our outcomes down into only 2 outcomes, not more than that. So other examples they're talking about here, you can think of a medical treatment. Either it's effective or it's ineffective. A person can be classified as having normal or abnormal blood pressure. So again, breaking it down into 2 outcomes. They're talking about multiple choice questions. So if you have a multiple choice question, you know, which has 4 or 5 choices, basically the idea is you can break it down into, did they get the correct choice or did they, you know, get the incorrect choice? So binomial experiments is what, you know, they're going to be talking about this, and you'll see this here in this little box over here. So they're saying situations like these are called binomial experiments. Each experiment, each repetition for the experiment would be called a trial. So you should have a fixed number of trials. So how many times you're going to be repeating that experiment, that should be a fixed number. Like I said, you should only have 2 outcomes, or you should at least be able to reduce it down to 2 outcomes. They are talking about these outcomes can be considered as either being success or failure. the outcomes of each trial must be independent of one another. So if you did one experiment, the results you get from that experiment should not affect what the results you will get if you repeat that experiment. So that's basically what they're saying in number 3. And they're saying the probability of a success must remain the same for each trial. So if you think about this last one here, and again, we'll go to our coin toss example. They're basically saying if you have, tossing a coin and you're going to get a heads or a tails, the idea is that probability should always remain the same. So if we're talking about, if it's a multiple choice question, like we said, maybe you have 4 different choices to choose from. Obviously the probability of success, if it's only going to be one option out of the 4 given multiple choice options you have, then obviously then your rate of success is going to stay the same, or in this case, the probability of success will stay the same. So again, with each trial, that probability should not change. So these 4 requirements are going to be very, very crucial, when we're talking about these binomial experiments over here. Now, when they're talking about, you can think of these outcomes as a success or failure, they're basically saying the word success does not imply something good or positive has occurred, because, we're using success in terms of, what experiment you're looking at, and it's going to keep changing with each experiment. So they're saying in the probability experiment, we might want to select 10 people and let S represent the number of people who were in an automobile accident. So basically, if we're talking about the number of people who were involved in an automobile accident, of obviously in this case, success is not going to be a good thing or a positive thing. We're just saying in this experiment, we are interested in knowing what is the probability that a person would, have an automobile accident. So that would be our success. Failure in this example would obviously be people who did not or who were not involved in an automobile accident. So that would be your failure. So that's kind of how we are looking at the success or failure description. So they are saying here in example 1, decide whether each experiment is a binomial experiment. If it's not, give a reason why. So selecting 20 university students and recording their class rank. So, one of the more important things is, are you able to break this down into only 2 outcomes? So is that even a possibility? Ranking the university students based on their class rank. What do we mean by class rank? Because, if you don't understand that terminology, then the question might not make sense. We're classifying students based on what class they are in. So are they, in a freshman class, sophomore class? That is what they mean by the class rank. Oh, Lily, I just saw your message about having the handout in D2L. Okay, I'm glad you remember that because I did not. So selecting 20 university students and recording their class rank, can we think of this as being a binomial experiment? Yeah, no, it's not, because like I said, class ranks we're talking about, are they a freshman, sophomore, junior, senior, and for that matter, if it's a university, they could also be a graduate student. So since this can be broken down into more than 2 outcomes, this is definitely not a binomial experiment. Selecting 20 students from a university and recording their gender. And other than the 2 outcomes, we also want to make sure, we're satisfying these other 3 requirements. So there should be a fixed number of trials, which of course this is fixed number because we're only looking at 20 students from the university. The outcome of each trial must be independent. So that's also going to be true, because if you keep selecting 20 students, are they going to be male or female? They're just going with that binary gender, that outcome is not going to be affected, and obviously the probability of success will remain the same. So all 4 requirements are satisfied, so we can say yes, this is a binomial experiment. Drawing 5 cards from a deck without replacement and recording whether they are red or black cards. So part C, what do you think? Okay, Lillian, why is that? Why would you say this is not binomial? Jesus, you are saying yes? So if you think about this, we can have a fixed number of trials, so that first one would be satisfied. We can break this down into 2 outcomes because they're talking in terms of selecting a red or black card. But number 3 is, sorry, not number 3, number 4, because even the outcomes of each trial will remain independent, but it's 4 where your probability of success will not remain the same. And the key word here, guys, is without replacement. So like Lily mentioned in her comment, the probability of success isn't the same because we're not replacing the cards. Because remember, we had talked about these being as dependent events. So when you're not replacing the card, your probability will keep changing. So that's actually where this experiment fails, and this is not a binomial experiment. Part D, selecting 5 students from a large school and asking them if they are on the dean's list. Selecting 5 students and asking them if they are on the dean's list. Is this a binomial experiment or not? Alexander, Lily, okay, you guys are saying yes. Yeah, so again, you have fixed number of trials. Obviously, there will only be 2 outcomes. You're either on the dean's list or you're not. So we are able to break this down into 2 outcomes. The outcome of each trial will be independent. Yeah, because selecting first 5 students, selecting from the other 5 students is not going to make a difference in your outcomes. And then, of course, your probability of success will also remain the same. Okay, very nice. And the last one, part E, recording the number of children in 50 randomly selected families. Recording the number of children in 50 randomly selected families. Lily, you're saying no? Okay, and why is that? Yeah, exactly. You can have a large variety of numbers because if you think about it, one family could have no children, so there would be 0. Somebody could have only 1 kid, you know, another family could have 2 kids, 3 kids, 5 kids, 7 kids, you know, whatever it will be. So this is where actually you will not be able to break this experiment down into only 2 outcomes. And so that's why this here obviously is going to end up failing, and you're not going to have a binomial experiment in that sense. Right, very nice, Lily. And of course, you can see the answers and the explanation over here. So they are saying a binomial experiment and its results give rise to a special probability distribution, which is what we call as the binomial distribution. So they are saying the outcomes of a binomial experiment and the corresponding probabilities of these outcomes are called as a binomial distribution. So they are saying, you know, like we talked about with binomial experiments, you can think of your outcomes as being either successes or failures. We talked about the multiple choice example. So they're saying the correct answer would be considered a failure. And of course, all of the incorrect answers, the other choices would be considered as failures. So you can kind of think of it, your success and failure in that sense. They're saying the notation that is commonly used for binomial experiments and binomial distribution are going to be probability of S, of course, is going to be for the probability of success. Probability of F will be the probability of failure. As a numerical probability, we can use the variable P for probability of success. So that's this little equation over here. And you can think of as Q being your numerical probability of failure. And the easiest way to calculate Q is to do 1 minus P. So again, you're actually using that idea of complementary events here again, because again, we know together the probability of success and failure is going to add up to 100% or basically 1. So together P and Q, which is your probability of success and failure, adds up to 1. So to calculate the probability of failure, you can basically do 1 minus P to come up with that. N would of course represent what total number of trials are being performed, and capital X here of course would be the number of successes out of a total of the N trials. So remember, your X value can be anything between 0 and N, including the endpoints. Now, when we're talking about calculating these probabilities for each of these events or outcomes, we're talking about this formula over here. So P of X, where X represents the the number of successes out of those N trials. You can kind of see that definition here. You're going to have N factorial, N minus X factorial on the denominator, and then you're multiplying that fraction by P raised to the power of X times Q raised to the power of N minus X. So this little part over here, this factorial part, is actually your combination examples. If you were to rewrite this, you can actually write it as combination with N as our total number of experiments or trials, and then X being how many successes we have from that, and then you're multiplying that with P raised to the power of X and Q raised to the power of N minus X. So this is basically, that first part is just a combination formula over there. So let's take a look at how this formula works out. We're talking about tossing a coin 3 times, and we want to know what is the probability of it getting exactly 2 heads. So of course, if you're tossing the coin 3 times, they're talking about what different outcomes we can have. And we have looked at this sample space. I think it was section, I can't remember, it was section 5.1 or 5.2. But you can see if you toss the coin 3 times, all 3 of them could land on a head, all 3 of them could land on a tail. You could have 2 of them which land on heads and 1 of them on a tail, or of course 2 of them could land on tails and 1 of them can be a head. So when you look at the sample space, the way we have it over here, you can see the probability of getting exactly 2 heads is going to be 1, 2, and 3. So that's a probability of 3 out of 8, or as a decimal point, 375. Now to use it with our formula over here, they're talking about, we do have a fixed number of trials because we're only tossing the coin 3 times. So we do have that. The outcome for this experiment would of course be they either land on a head or a tail. So we do have those 2 outcomes. So it satisfies that. The outcomes are of course going to be independent of one another. So we're saying the outcome of one toss will not affect the outcome of another toss. So we know the events are independent from each other. And our probability of success, and in this success is the probability of getting ahead, is always going to stay 1/2. So we are satisfying all 4 of those binomial experiment requirements over here. So you are talking about tossing the coin 3 times, so that's N equals 3. We are talking about X as being 2 because we want exactly 2 heads, so that's X equals 2. We know the probability of getting a head is 1/2, which means the probability of not getting a head would also be 1/2, which of course in this case would mean the probability of getting a tail. So you've got your N, X, P, and Q value. So now you can plug it into this formula over here and you can see how that ends up looking like. So this again, remember, is your combination. So that's combination with 3, and you're choosing 2 of those events, and then P raised to the power of X, Q raised to the power of N minus X, and you will see we still end up getting the exact same answer. So you do have the binomial probability formula, And of course, we do have that table that I just sent you guys, but we'll talk about that here in a minute. And you can kind of see the little description that they are going through over here. You can see they're talking about the combination and how that combination will end up looking like. So I've gone over all of this with you, but if you want to kind of read through that, you're obviously welcome to do that. Okay. So they're basically saying to generalize, each success has a probability of P and that can occur X number of times, and each failure in this case also has a probability of Q, and that will occur N minus X times, and that's what they're actually talking about here in terms of this second half of our formula over here. And of course, when we are talking about getting sampling done without replacement, remember this is where they will have dependent events. So they're talking about, however, the events can be considered independent if the size of the sample is no more than 5% of the size of the population. So we're basically saying your sample size will not be greater than 5% of your population size. So it can be 5% or less than 5% of the population, but not more than that. So they're saying when sampling is done without replacement, these events can be considered as independent if your sampling size is less than, or basically it's not more than 5% of the population. And we're saying the reason is that when one item is selected from a large number of items and not replaced before the second item is selected, the change on the probability is so small that it does not actually affect your probability at all. So your sample size, is in some examples, they will actually have you check to see if you are meeting that requirement of being, 5% or less than 5%. So let's take a look at this example here. They're saying a survey found that 1 out of 5 Americans says he or she has visited a doctor in any given month. If 10 people are selected at random, find the probability that exactly 3 will have visited the doctor in the last month. So in this case, we are talking about randomly selecting 10 people, so that's your N equals X. We know if exactly 3 of them would have visited a doctor or not, so that's our X value being equal to 3. They are telling us 1 out of 5 American has visited a doctor, so that's your probability of success, because obviously they want to know when was the last time these 3 people had visited doctors. To calculate your Q, remember they're basically using the 1 minus P calculation, so that's 1 minus 1/5, which is how they came up with this 4/5 value from, and then they're plugging it into the binomial experiment formula over here, and this is coming out to be a probability of 0.201. Remember, in decimals we round them to 3 decimal places, so that's a probability of 0.201 that if you selected 10 people randomly, exactly 3 of them would have visited a doctor in the last month, and you can see that's a pretty small probability over there. Okay. Example 4 here is talking about a survey from Teenage Research Unlimited in Northbrook, Illinois, found that 30% of teenage consumers receive their spending money from part-time jobs. So if we're selecting 5 teenagers at random, what's the probability that at least 3 of them will have part-time jobs? So the one thing you should notice in this question is this one here said exactly 3. This one here is saying at the least 3. So they are talking about basically for the at least calculation, it is necessary to find the individual probabilities for the 3, 4, or 5 out of these 5 teenagers that they have selected, and then add all of those probabilities together. So we start by taking the probability of P of 3, plug it into the formula, get your probability value. We repeat that calculation with X equals 4, find its probability, and X equals 5, and find that probability, and then you actually add all three of them. Because you know, when we are saying at least three, that means out of those 5 teenagers we are selecting randomly, if we are saying at the least 3 of them should have a part-time job, that means 3, 4, or 5 could have part-time jobs, right? Because we're talking about at least, which means at the minimum 3 of them should have a part-time job. So that's why we have to actually do this calculation for P of 3, P of 4, and P of 5 and add those probabilities together. So they are saying computing probabilities by using the binomial probability formula can be tedious, like we saw in this example, because we had to do it 3 different times. So you can actually also use those tables for the binomial distribution, where you need to know your n and your p values. So in this case, this is our table B over here. So you can see we have our n value on the leftmost column. You have your probabilities here on the top row. And then depending on what x value you have, you can actually select what that probability is going to be. The only problem with this table, guys, is you will see your probability is restricted, because your probability can be at 0.05, 0.1, 0.2, 0.25, 0.3, 0.4, 0.5, 0.6, 0.7, 0.75, 0.8, 0.9, and 0.95. So if you know some event had a probability of like 0.67, then you will not be able to use this binomial distribution table over here. So you just kind of have to be careful of when you need to use the formula and when you can use the table. If it's any of these probabilities that they are giving you here in the table, definitely use the table, because it will make your life go faster. The example would go a lot quicker. But if you don't have that option, then of course you have to use this binomial probability formula over here. So I think this next example is just kind of showing us how to use the table over here. So this is going back to this example 2 that we have looked at right at the beginning, where we were tossing the coin 3 times and we were looking for exactly 2 heads. So in this case, your n value equals 3, x equals 2, and we know the probability of getting a head is 1/2, so that's your 0.5. You can go 0.5, obviously it's part of our probability distribution table. So what you would do is go to the leftmost column, find n equals 3, then from that you would find x equals 2 and go out till you hit that probability of 0.5. And again, you will notice it's that same number of 0.375. Again, look at the table. Our n value is 3, x value is 2, probability is 1/2 or 0.5. And you can see when those rows and columns meet, you are at that 3/8 or 0.375 value over here. So, obviously for this example, you can use the table. So I'll have examples for you where we will need to use both the formula and the table. So let's take a look at these last couple examples, and then we'll look at examples from the textbook over here. So we've got this one here talking about public opinion reported that 5% of Americans are afraid of being alone in a house at night. So if a random sample of 20 Americans is selected, find these probabilities using the binomial table. So if you are selecting exactly 5 people out of these 20, so we want to know what that probability would be. So in this case, your n is 20. They are telling us 5% of the Americans are afraid, so that's our probability of 0.05. And then in part A, they're saying exactly 5 people, so that's of course x equals 5. So you've got n of 20. There we go. So n is 20. They're telling us exactly 5 people, and our probability is 0.05. So from right here, you can see you've got 0.002. Now, the other thing I want to point out is you will see how there are all these blank spaces over here in this table. So what it actually means is for these blank spaces, that probability is going to be 0.000. So anywhere where you have blank spaces, just remember all of these probabilities are 0 because they are so small that they just haven't included. So just kind of keep that in mind as you're looking through these tables over here. So you can see from the table, we are getting 0.002 as our probability. So that's where they got this number from. For part B, they are asking us there are at most 3 people in the sample who are afraid of being alone at night. So this time they're talking about at most, which means maximum. So one thing I want to point out is look at how we are using these inequality symbols. So for this guy, part A, where they had exactly 5 people, you would have x equals 5 as your notation. Part B, they said at most 3 people, so that's a maximum of 3 people. So you do x is less than equal to 3, which means the maximum is 3 people, but you can also have less than that. So you have to do 0 people were afraid, only 1 person was afraid, 2 were afraid, or all 3 would be afraid of being home alone at night. So you would then have to do n equals 20. Of course, probability is still 0.05, but now you would be taking the values for 0, 1, 2, and 3. So that would be 0, 1, 2, and 3. So you would be taking all 4 of these values and adding them together. And you can see that total comes out to be 0.984, which is a pretty high probability. I mean, you are talking about 0.984 probability that at most 3 of those 5 people would be afraid. 3 out of the 20 people would be afraid of staying home at night. So that's a pretty high probability here. Part C, kind of the example we just looked at, this is talking about at least 3 people. So when we are talking about at least 3 people, if you look at the description over here, of course, n is 20, probability is still 5%, 0.05. So when we're saying at least 3 people, that means anywhere from 3, 4, 5, all the way up to 20 out of that sample size of 20 could be afraid of, staying home at night. That's a lot of individual numbers to calculate. So the easy way to do is, again, use the complementary event. We know when you're talking about at least 3 people, that means it's 3 or more. So since it's 3 or more, it's actually going to be easier to take the probability of 0, 1, and 2, get that total, and then just subtract it from 1, and you will get your answer of 0.076. So we're again using the idea of probability of an event by using a complementary event to calculate these. And this is really going to come in handy because, that's going to be a lot of numbers you would kind of have to add up. Now, in this case, you, of course, wouldn't have too many because other than probability of 3 to 5, which gives you numbers, the remaining of these, of course, are going to be zeros. So for this particular example, it wouldn't be as bad because you would only have to calculate these 3 numbers. And if you add that 0.060, 0.013, and 0.002, you will see all of those also add up to the same value of 0.076. So you could have come about it that way, but what if you were using a different data value? Where you had, a lot more numbers to add up, that would definitely be a lot of numbers, you would kind of end up adding together. So, we normally try to use complement of the events when we can. Just a couple more examples over here. This one is talking about a report from the Secretary of Health and Human Services stated that 70% of single vehicle traffic fatalities occur at night on weekends involving an intoxicated driver. So if you have a sample of 15 single vehicle traffic fatalities and you're selecting these randomly, what's the probability that between 10 and 15 inclusive, which means you're including the endpoints of 10 and 15, the accidents that happened involved a driver who was intoxicated? So since this is talking about out of a sample of 15, you are looking at, anywhere from 10 to 15 single vehicle fatalities. That means you would be doing your calculations for each one of these X values. And in this case, of course, our sample size or trial number of trials is 15. Our probability, they are telling us, is 70%, so that's 0.70. And then you're looking at all of these different X values. So N equals 15. And your 70% is this column right over here. Okay, so N is 15, and then our X values are going from 10 to 15. So that's going to be these numbers over here. You're going to basically add all 6 of those numbers, and you can see when we add them up together, it adds up to 0.723. So, pretty high probability. Again, it's higher than 0.5 or 50%. So we're saying the probability that between 10 to 15 drivers who were in a traffic fatality would also be intoxicated, and that probability is 0.723. So yeah, really bad probability over there. So let's take a look at some examples on calculating these binomial probabilities, and then we'll come back and talk about the mean, variance, and standard deviation. So, oops, looks like I timed out over there. Okay, so let's start out with first recognizing if we have binomial experiments or not. So let's start with number 1. And this one is talking about surveying 100 people to determine if they like sudsy soap. So can we break this down into a binomial experiment? Remember those 4 requirements that we have looked at? Let me just bring this up quickly. So fixed number of trials, they should be able to have only 2 outcomes or break it down into 2 outcomes. The outcome for each trial should be independent from one another, and your probability of success should remain the same for each trial. So keeping those 4 requirements in mind, what can you say about 1A? Alexander, you are saying yes? Yeah, because we do have a fixed number of trials. They're telling us we are surveying 100 people. Jesus, Kimberly, Lily, all of you are saying yes, okay. So you can break this down into 2 outcomes, right? Whether they like sudsy soap or they don't like sudsy soap, you can break it down into 2 outcomes. And then, hopefully if you are selecting these people at random, one person's answer should not affect the other person's answer. And so your event should be independent and your probability of success should remain the same. So yeah, very good. We can say yes. We can reduce this down to binomial experiments. Tossing a coin 100 times to see how many heads occur. Part B. Kimberly, you're saying yes. Jesus, yes. Alexander, yes. Okay. So again, you have a fixed number of trials. We're tossing the coin 100 times. You either get a head or a tail, so 2 outcomes. And again, each coin toss is going to be independent. So the last 2 requirements would also be fulfilled, independent, and the probability of success would remain the same. Drawing a card with replacement from a deck and getting a heart. So part C. Alexander, you're saying no. Okay. Drawing a card with replacement from a deck and getting a heart. So do we have a fixed number of trials, which technically in this case, it is going to be only one trial, right? Because you're only drawing a single card. Jesus and Kimberly, you guys are saying yes. So limit fixed number of trials. Now, as far as your outcomes go, you can actually break this down into two outcomes, right? Whether you got a heart or you did not get a heart. So we don't care what the other cards are. We're only interested in if you got a heart or not. So that would definitely be two outcomes, heart and no heart. As far as your events being independent, they are actually going to be independent because they are telling us that we are replacing the card. We are putting the card back into our deck. So your events will be independent, and which also means our probability of success will remain the same. So Alexander, does that make sense why this would actually be? Okay, you were thinking there wouldn't be just one trial. Okay, I can kind of see that. Alrighty, what do you think of part D? Asking 1,000 people which brand of cigarettes they smoke. Kimberly, Jesus, you guys are saying no. Alexander, no. Okay, do you want to give me a reason why this couldn't be a binomial experiment? Yeah, very nice. That's kind of what I was thinking also, is that, you know, there are so many brands of cigarettes, because unlike the Satsi soap example, they're not saying, do you like this brand or you don't like it? So yeah, since there can be more than two brands of cigarettes, we cannot actually break this down into a binomial experiment. Very nice. And part E, testing 4 different brands of aspirin to see which brands are effective. Okay, Kimberly, you're saying no for the same reason as above. Lily, you're also saying no. Testing 4 different brands of aspirin to see which brands are effective. Yeah, because you know what's happening here is you have 4 brands. Now, if they were talking about, you know, one brand and wanting to know if it is effective or not effective, yes, that can be simplified into a binomial experiment. But when you're talking about 4 brands, you know, it's going to be hard to just break it down into a binomial experiment. Yeah, very nice, guys. Alrighty, good job. Let me save this, clear it out, and let's do this one more time very quickly for number 2, and then we'll move on to our solving problems. Testing one brand of aspirin by using 10 people to determine whether it is effective. So you can kind of see it's a different take on that 1E example we just did. So testing one brand of aspirin by using 10 people to determine if it is effective or not effective. Jesus, you're saying yes? Alexander also, okay. Yeah, because this one, like I was saying before, you know, since they are breaking it down to just one brand and they want to know if it's going to be effective or not effective, so that's 2 outcomes. We are keeping a fixed number of trials because we're using 10 people. And then let's see, the probability of our success and our events being independent should definitely also work, because again, you know, you would be choosing those 10 people randomly. So yeah, this guy can be broken down into a binomial experiment. Okay, part B is saying asking 100 people if they smoke. Alexander, you're saying yes? Asking 100 people if they smoke. Jesus, you're also saying yes. Yeah, because you have fixed number of trials with those 100 people, Lily, okay? Yeah, so your 2 outcomes can be they smoke or they don't smoke. So those could be our 2 outcomes. And again, we will be able to maintain independent trials. And then of course, probability of success will remain the same. Checking 1,000 applicants to see whether they are admitted to White Oak College. 1,000 applicants to see if they were admitted to this college. Jesus, you're saying yes. Alexander also. Okay, so 1,000 applicants, that's our fixed number of trials. They either got admission or they did not, so that could be two outcomes. And then, yeah, I mean, one student getting accepted will have no effect whether the other student gets, admitted or not. So you would have independent events, and then again, your probability of success will remain the same with each trial. So very nice. C is also going to be a yes. Surveying 300 prisoners to see how many different crimes they were convicted of. Part B. Alexander, no. Kimberly, no. Lily, no. Okay, so can you give me the reason why this is no? So where is this failing at? Yeah, there's so many different types of crimes they could be convicted for, right? I mean, it could be uh, Grand Theft Auto kind of thing. It could be obviously, murder or homicide or that kind of thing. So yeah, I mean, there can be so many different reasons, burglaries and stuff like that, why they ended up in prison. So that would be no. Part E, surveying 300 prisoners to see whether this is their first offense. So kind of similar take from part D, but they're just changing the result here. So whether this was their first offense or not. Alexander, you are saying yes. Okay, so we do have fixed number of trials because again, we are taking a survey of 300 prisoners. Jesus and Kimberly, you guys are also saying yes. Now they want to know if this is their first offense or not, right? So in this case, either it is or it is not. So you can break it down into two outcomes. What one prisoner says will have no effect on the other prisoner, so your outcomes will be independent. And then of course, your probability of success will also remain the same. So the only no was that part D over here. Everything else, we can use binomial experiments with those. Alrighty, very nice. Let's see the next example I wanted to look at. How about, just to make sure you guys are going to be comfortable, let's do 3B over here. So if you would, since you guys have the table, why don't you go ahead and tell me what this answer comes out to be when you use the table? So n equals 4, probability of 0.60, and x equals 3. Okay, Alexander, you've got 0.346, so let's go to our table over here. Okay, so n equals 4. Okay, you've got n equals 4. Probability of 0.60 and x equals 3. I'm gonna flip this guy a little bit. Okay. So yeah, if you look at where those two would intersect for x equals 3 at n equals 4 and a probability of basically 60%, 0.6, you are getting 0.346. So this is going to be our number over here. So you can see it's really, really straightforward, when they're asking you to use the table in this case. Now, how about one with our binomial formula? So that, again, we can make sure you are comfortable working with these. And you should notice, all of these probabilities that are given to us, either in example 5 or example 6, look at those probabilities. You know, none of these are going to be in our binomial distribution table. So, you know, that's what kind of what I was saying, that when you look at these examples and your probability doesn't come out to be, you know, any one of these that match our table over here, that by default tells us we want to use the formula. So how about we go ahead and do, I guess it really wouldn't matter. But let's do B again from number 5. So let's do 5B. So this would be basically finding the probability for x equals 2. Remember, that's n factorial, n minus x factorial with x factorial, or basically taking a combination with 4 and 2. And then taking your probability of p, which is 0.18, you raise it to the x power, which is 2. Now we also need to know what q is. So if p equals 0.18, what is the q value here, guys? Yeah, very nice, because you would have to do 1 minus p, which would end up becoming 1 minus 0.18. So that's 0.82. So that's going to be 0.82. And remember, that's n minus x. So basically your exponent would be 4 minus 2, which obviously also comes out to be 2. So you're basically taking the combination with 4 and 2, and then you are taking 0.18 raised to the second power times 0.82 raised to the second power. And what does that come out? So I'm going to use the combination key on my calculator to do that first part. Okay, so get the answer from that, and then just multiply with 0.18 raised to the second power times 0.82 raised to the second power. And then remember, your rounding rule is 3 decimal places if you don't have a bunch of zeros in the beginning. So once you have that answer, let me know. Jesus, I did not get that. Alexander, you got point. Okay, Jesus, got it. 0.131, yeah. Because my raw answer is coming out to be 0. Let's see. 1307 1456, but we're only interested in 3 decimal places, so this would come out to be 0.131, like Alexander said. Yeah, very nice, Jesus. Okay, very good. Lily, you got the same thing. Yeah, very nice. So with 3 decimal places, you are looking at approximately 0.131 as your probability for getting a success of x equals 2 out of a total of 4 trials. So this was just a basic, you know, examples to get us used to working with the formula and the table. Now let's look at some application examples over here. So let me clear this one out, and let me see which one do I want to work on. How about we do number 8 over here? So your instructions are: assume all variables are binomial. If the values are not found in table B, use the formula. So looking at number 8 over here, they are saying a student takes a 20-question multiple choice exam with 5 choices for each question and guesses on each question. What's the probability of guessing at least 15 out of 20 correctly? Would you consider this event likely or unlikely to occur, and explain your answer. So let's talk about how many total trials do we have in here. Let me clear this. There we go. So what's our n value? What's the x? What's the p? And I don't know if we need it or not, but let's go ahead and calculate the q also. So what do you think is, how many total trials do we have? N equals what? So it's a 20-question test that has multiple choice of 5 choices in each. And what's the probability that the student would get at least 15 out of the 20 correct? Okay, so Lily, you've given me n equals 20, p equals 0.5, q equals 0.5, x goes from 15 through 20. Okay, some parts of that are correct, some parts are incorrect. Does anybody want to help Lily out here? So we know it's a 20-question test, right? So yeah, definitely you have a total of n equals 20. So that part was correct. What else? Let's look at that probability here again. What are they telling us about the type of questions? Very nice, Lily. Yeah, because they're telling you it's a multiple choice exam, which has, each question has 5 choices, right? So out of those 5 choices, of course, only one of them would end up being correct. So that would actually be a probability of 1/5, or as Jesus has here, 0.20. And then of course that means the probability of not getting the right answer would be 0.45 or 0.80. But you know, 0.20 is a number you can find in the binomial table. So technically we don't really need the Q since we wouldn't be using the formula. Now, as Lily had mentioned, they are telling us it's at least 15 out of the 20 questions that are correct. So this would actually then be that your x is greater than or equal to 15, because at least 15 are correct, but it can be 16 is correct, 17 is correct, 18, 19, 20 is correct. So let's go ahead and see what each of those probabilities would be. So you are looking for probability for x equals 15. Okay, so for x equals 15, for x equals 16. You can start looking at these if you want in your table and give me the answers for each of these probabilities. Let me see what you come up with. Alexander, you've got 0. Okay, so our n value is 20. And it starts at 15 going all the way to 20. And a probability was 0.2. So you're looking at probability of 0.2. N equals, oops. N equals 20, and then x goes from 15 to 20. So yeah, you're basically looking at a bunch of zeros over here, right? Because they are blank spaces. So all of our probabilities are going to be zeros. So you can obviously see by the time we get done adding all of these, the probability of x greater than equal to 15 is basically you're taking 0.00, and how many are these? 1, 2, 3, 4, 5, 6. You're multiplying it 6 times, which would still give you a probability of 0.000. And I'm keeping that 3 rounding space the same. So guys, the question here was, would this event be likely or unlikely to occur? So what would you say about this? Yeah, I mean, more than unlikely, we would almost say impossible, wouldn't we, with the probability of being 0.000. So yeah, this is, oops, highly unlikely, or almost impossible at 0.000. So that is basically if we had to pick students who got at least 15 out of the 20 questions correct. That's a very, very unlikely scenario that's what happened. Okay, so number 8, you can kind of see how this answer came out to be. Now let's look at, let's do number 14 over here. Okay, so this one is talking about 26% of couples who plan to marry this year are planning destination weddings. I guess this does not apply to 2020, I guess, since nobody's going anywhere. All right, so in a random sample of 12 couples who plan to marry, what's the probability that exactly 6 will have destination wedding, at least 6 will have a destination wedding, and fewer than 5 will have a destination wedding? So let's identify our N, X, P, and Q values. So what would you say is the N value here? There we go. Alexandra, Lily, you guys have 12. Yeah, because they're telling us it's a random sample of 12 couples, right? So that's 12. Very good. We'll come back to the X value in a minute. What's our probability here? Very nice, because that's how they started the example, right? They said 26% of couples who plan to marry will have a destination wedding. So this is a probability of 26%, or 0.26. And you can of course see 0.26 is a number which would not be part of our binomial distribution table, right? So we're going to have to use the formula. So we definitely need to know the Q value. So can you tell me what that Q value is going to be? Very nice, Lily, 0.74. And then, of course, our X value is going to keep changing based on parts A, B, and C. So let's start with the first part. This is where they are saying exactly 6 couples. So that means X equals 6 in this case. So this is finding a probability for X equals 6. We will have to use the binomial formula because of that 26%. So that's going to be 12 factorial on the top, 12 minus 6 factorial, 6 factorial on the bottom, and then multiplied by probability of 0.26 raised to the x value of 6, and q, which is 0.74 raised to the value of n minus x, so that's 12 minus 6. So again, you are doing combination on the first part between 12 and 6, then multiply by 0.26 raised to the 6th power, 0.74, which is also raised to the 6th power in this case. So what do you think this answer will end up looking like? Maybe you've got 0.047. Okay, anybody else? Because again, you can use the combination for that first part and then just multiply by those exponents. So Jesus, you're giving me 0.0468708, okay? So 3 decimal places will bump it up to approximately 0.047 already. Very good. So it's still a pretty low probability that if you select 12 couples randomly, half of them would have a destination wedding, right? Because that's what, barely a 4.7% probability. Okay, let's see. Part B in this question was asking us at least 6 couples will have a destination wedding. So at least 6 couples. So that means, of course, we are saying X is going to be greater than or equal to 6. So this technically means you're looking at 6, 7, 8, 9, 10, 11, 12, right? Each one of those individually. So you can do the binomial formula for each one of these numbers, or you can use the idea of a complement. So that's where you would do probability of 0, 1, 2, 3, 4, 5, and then subtract that total from 1. So why don't some of you try the direct route of going 6, 7, 8, 9, 10, 11, 12, and some of you try going 1 minus probability of 0, 1, 2, 3, 4, 5, so you can compare and see if you're going to get the same answer or not. So for probability of x being greater than or equal to 6, you can do probability of 6 plus 7 plus 8 plus 9 plus 10 plus 11 and plus 12, or you can do 1 minus probability of 0, 1, 5, and then subtract that total from 1. So whenever you have your final answer ready, just let me know. Okay, let's see. What do you have? 0.064. Okay, can somebody verify that number for me, please, if you have your final answer? Looks like these last ones are actually just coming out to be a bunch of zeros. Alexander, okay, you got 0.065. So Lily, can you tell me which method did you go with? Did you do the P of 6, P of 7, P of 8 all the way to 12, or did you do 1 minus? P of 0, P of 1, P of 2, that route? Because if you do the first one, which is the numbers that I have here in red, these ones will add up to give you, so for the first method, you are actually going to get 0.064. But if you did the other way, you did the second method, so you did 1 minus P of 0, Alexander. You did not do the complement way. So Lily, you did each individual numbers from 6 to 12 and then added them. Yeah, so that's actually what I wanted to highlight over here, guys. When you do it the traditional way, going from 6 to 12, you are actually going to get 0.064. But if you do it the other way, which is your P of 0, 1, 2, 3, 4, that actually comes out to be 1 minus 0. I cannot read my own handwriting, 0.935. So this actually comes out to be 0.065. So there is going to be a little bit of an answer difference. And you can see it's really 6.4 or 6.5%. So there's a slight chance difference depending on which way you go and how you do your calculation. But, you know, I mean, that's just how this is going to work out to be, unfortunately. So it does come out to be slightly different depending on which process you use. As far as Connect Math goes, I'm honestly not sure which process would make a better answer. So this might be something you might have to try. If it accepts both the answers, that'd be great, because technically it should. But sometimes they do things we don't expect them to do. Okay, so we also have part C, which said fewer than 5 couples have a destination wedding. So when they're talking about fewer than 5 couples, of course, we are saying X is less than 5. So in this case, that would mean 0, 1, all the way to 0, 1, 2, 3, and 4, right? Because they're saying fewer than 5, which means you're not including 5 in there. So you're actually just taking the probability of 0, 1, 2, 3, or 4 of those couples having a destination wedding. So those of you who did it this second way, you should already have these numbers. So Lily, sorry, unfortunately, since you did the 6, 7, 8, you would have to go back and calculate these individual probabilities. So what will that come out to be, guys, this total? So for each individual, just make sure you're rounding it to 3 decimal places and then add them together at the end. Okay, so what do you guys have for that? What did you get for probability of 0? Alexander, what did you have for probability of 0? And do the rest of you have the other numbers? Okay. Yeah, very nice, Jesus. So in 3 decimal places, that would be 0.027 for probability of 1. And these probabilities will keep increasing as you go from 0, 1, 2, 3, 4, and 5. So they will keep going a little bit higher each time. You guys don't have those numbers yet? And again, what I do is I type in once in my calculator, and then I just keep going and changing those numbers as my X value keeps changing. So for probability of 1, what do you have? Very nice, Lily. 1, 1, 4. Okay, probability of 2. Yeah, very nice, Lily. It actually comes out to be 0.2196, so that at 2196 actually ends up going to 0.220. So very nice. Probability of 3 again will be a number slightly larger than that one. And again, since we are actually after 1 o'clock, I'm going to go ahead and give you these numbers, but make sure you know and you are comfortable calculating these. But actually now for P of 4, it's going to drop a little bit. You're going to have a probability of 0.203. So by the time we add all of these, 5 probabilities together, it actually ends up becoming a probability of 0, 0 point, what is that total? 821. So those of you who would have done 1 minus P of 0, P of 1, P of 3, 4, and 5, what you could have done is if you had this total over here, from that total, you could have just subtracted the probability of 5, and that should have also given you this number of 0.821, because, you know, obviously in this case, they are all related depending on which one you do. So just kind of keep in mind on how they give you the question. So like here, when they say exactly 6 couples, at least 6, or at most 6, or, you know, fewer than 5, each one of those is going to have its own individual calculation. And then based on what your probability is, you can kind of decide, you know, can I use the probability table, or do I have to use the binomial probability formula? So I do have a couple more examples that I would like to talk about this. So we will do that tomorrow. So just to give you guys some time, since we, you know, just kind of did half of chapter 5 last time and half of chapter 5 today, how about I make Wednesday the exam day for chapter 5? Is that okay for you guys, or would you like to do it tomorrow? Wednesday? Kimberly, you're saying Wednesday, okay? Are the rest of you also okay with that then? It gives you 1 extra day to kind of do the homework. Lily, you want to take it today? Okay, why don't you give me about half an hour to make sure I have it set up and everything, and I'll go ahead and set it up and send you an email, okay, on D2L. So the rest of you guys are comfortable with Wednesday then? Okay, so yeah, just, you know, let me know what time you would like to take your exam on Wednesday. You can let me know tomorrow, okay? All right, guys, be careful, stay safe, work on your homework, and let me know if you have any questions, okay? Bye. Take care, everyone. Bye-bye.